Tomasz Widomski holds degrees in computer science from the Warsaw University of Technology, economist from the Warsaw Business of Economics, and an MBA in cybersecurity from the Military University of Technology. He oversees the Elproma Time and Frequency Division, achieving significant international successes with its R&D team, including the CERN White Rabbit project, 2009 to 2013, Dimitra Horizon 2020, 2014 to 2016, and Giano Thales Alenia Space anti-spoofing authentication from the Galileo satellite. Tomasz specializes in professional time and quantum metrology and is an expert in cybersecurity, particularly in time synchronization attacks and time delay attacks. He is a member of the Atomic Timescale Laboratories in Poland TAPL and holds accreditation from the state of Poland for the ITU delegation working on the UTC timescale. He has contributed to EU security draft groups for DG Energy and DG Connect, and is a frequent lecturer at international conferences, including the NLPQT Quantum Key Distribution (QKD) project. In 2023, Tomasz successfully supervised the IZAS-PL N. E-Time-PL National Ground UTC Time Distribution project in Poland, providing an alternative to GNSS-REF. Source of UTC-PL time.
Hello.
Hello.
Well, good afternoon to everyone. So it was a great pleasure to listen to a presentation of Adam and Florian. The last third presentation will take you to a little bit different.
Please, Tomasz, if you can put in the full screen your presentation.
Oh yeah, sure. Sorry. I'm going to take you to
Perfect,
some journey that is a kind of a link, a conductor, because time, we are going to talk about the timing, synchronization. Furthermore, we are going to try to destabilize the quantum key distribution using the desynchronization technique. And this is the main purpose of this presentation, to show you a little bit Achilles heel of the advanced technology, of the modern advanced technology. My name is Tomasz Widomski. I'm working 30 years in the time and frequency business. We have been since begin with the quantum key distribution experimental part. Right now, we are assisting cybersecurity, where the timing became to be a kind of a new cyber weapon. So before I go to the details, I will briefly introduce the slide that is a very good point to start. So hacking RSA, normally it takes 6,000 billion years using a standard computers. It can be improved up to 21 billion years if you use a supercomputer. Of course, we are all afraid, feeling the brief of the quantum computing, that this can be done much faster in the 1-2 steps using quantum computers. But nevertheless, this let us compare about what kind of a timescales we are talking about and what is all about. The important conclusion of this picture for the attacking sides are two things. First of all, the attacker of QKD should not waste its time, definitely. Whatever the quantum computer exists or not, he should not waste time. It is because it is much more easier to destabilize the advanced technology than to hack it. That's definitely enough good reason, you know, to not waste your time. So what's the problem? What is the status quo of the QKD? We have been observed many laboratories and many companies working on the QKD, finding out that this group of the community has one specific vector. It is a big enthusiasm and tightly focusing on the technology, on the cipher technology. They can discuss hours about, algorithms, about coding, decoding, single photon technology, and so forth. And they are forgetting about many other things that are creating exactly the gap that can be used by the attacking side. So secondly, the QKD, I don't know if you have taken attention on the Adam Widomski presentation, but on the block diagram, I have catch the little subpart called synchronization. And this is really true that the more, at least the all solutions I know from the previous 30 years, the QKD is requiring synchronization. And beside that, to offer the resilient security, the QKD needs to be a self-defending cybersecurity solution. It needs to ensure the operationality 24 hours a day, which is a big challenge. So once again, combining together with the previous slide information, you should assume that the hackers today, more than hacking the codes and breaking the quantum cipher, they will definitely focus to push the system to no operational denial, equivalent of denial of service, something like that. So what I'm going to tell you during this presentation, it will be probably mostly something new for most of you, but I'm operating for many years as an accredited expert at ITU, and I can tell you that there is a special dedicated group. It's called WP7A, which is tightly dedicated to synchronization. And this group of the International Telecom Union is in touch with the networking group, with the energy group, telecom, and so forth. And we have found out a long time ago that timing seems to be a kind of a gap, security gap for all most important critical infrastructures today. So today I'm going to define two new ways of this synchronization attack. One is a typical time synchronization attack. The second one is time delay attack. But before that, we will also talk a little bit about the random generation, and then we switch to the pure attack and destabilization of the cipher. Okay, the very first tip we like to highlight is when you cipher something, probably the most important part of the cryptography is to have the real randomness. Therefore, any random generator, it doesn't matter whether they're quantum or classical, they should be well tested as well as short term as well as a long term for its randomness. Not having a real random, currently it reduces the performance, not the performance, but the trustability of the cipher itself. And this is something which is frequently very much forgotten because we mostly use the ready commercial random key generators. And this is something that we put a lower priority than the cipher itself. So whatever you design the scientific or the commercial solution, you really should think about the certification of your randomness. And that is provided by the several institutes of the measurements in United States, in Europe, and Asia, and so forth. So here are a couple of tips for the random number generations. First of all, of course, the quantum random generators are always better than random generators. The typical random generators, they mostly need some time for the initialization. So they need to warn the circuit to improve the entropy and to start the real randomness. Besides that, we have found out in the last years that a lot of laboratories, they transfer random numbers more than generate them locally. Even there is some service from NIST offering the random numbers generation, which can be imported or even read from the National Institute of Standardization. This is not a good idea. The random generation should always be a local one. Never send any data via network or any public connectivity. Of course, the initialization takes a long time. The best solution is if you want to switch your random generator and you keep it operating continuously, do not switch it off and so forth. But if you have to restart your random generator, take at least 12 to 24 hours to warm the generator itself. One of the very niche side effects and also the gaps, security gaps, is that bridging chipset that are providing the random generation can impact on the randomness. This is very well tested and proven in some chipset manufacturer already. So what is a random before bridging, it is not necessarily the same random after it. This is good to note for your real application environment deployment. Besides that, it's always a good practice to mix many different kinds of the generators using XOR function. So you can use at the same time the quantum as well as modern generators, classical generators together, it's not only improving the performance of the availability of random numbers, but it also reduces the risk of being dependent on the single supplier. You know, random generators, similarly to any other hardware and servers, they can fail. They're in a regular production. They pass the testing, of course, but if you want to build your robust solution, you should think more about the mixing the solutions. And beside that, the NIS2, which is the state-of-the-art resolution of the European community, it is obligated since October this year. We should control our supplier chain, how they supply, what about the quality of the components they supply to us, and so forth. So those are the practical tips when you build your own quantum key distribution or any other cipher you want to use to defend your IT systems. Okay, now we are going to transfer to the quantum key distribution in the aspect of the synchronization attack and delay attack. Here are a couple of facts. The first one is the quantum key distribution is requiring synchronization, at least those that has been designed and developed in the previous decade. It is perhaps the future of QKD to consider a solution that will not require the synchronization, but this is very, very hard to reach because currently both sender and the receiver, the Alice and Bob, they need to exactly operate in the same time and frequency domain. In some cases, this frequency and time domain, it is required to be more stable and more accurate than the parameters I have presented on the screen. Besides that, just to achieve the target of the 100 picosecond, there are oscillators used for the synchronization. And those oscillators, to ensure a time domain operation, they are mostly locked on the GNSS. Here comes the latest state-of-the-art risk of the desynchronization. Currently, we recognize jamming and spoofing attack on the GNSS signals, which are used to lock synchronization signals as the biggest challenge globally for all countries, including Europe and United States and Asia as well. Secondly, controlling your hardware can provide for some unexpected discoveries of innocent chipset that are mounted inside chipset. This is going to be a part of the last slide presentation. I have prepared a very special movie. I'm going to show you how this might look like. So here are the best practices. Of course, trusting is good, but controlling is much better. So provide the audits of existing hardwares, take a little percentage of the components you are using to build your own QKD and disassemble them. Sometimes it's necessary even to involve reverse engineering techniques to ensure that you get what you should get to build your own cipher. The highest risk remains on the GNSS, which is a very weak, especially GPS, American satellite system, but also the risk is on the LAN communication. And one of the, let's say, niche tips for this part is try to avoid a standard network synchronization. So now you can see the slide that is showing a kind of the risk for a time delay synchronization. On the left screen, you can see we are disassembling using laser some chips. More of the QKD manufacturers, they design their own chipset, and those chipsets can be manufactured. They are mostly manufactured outside of the original manufacturer of the hardware. So after disassembling chips, you can find a lot of interesting things. And on the right side, you can see there is a little chipset inside the bigger chipset. This chip has been located inside for a very specific purpose, just to generate a noise that will destabilize the frequency domain. And destabilizing the frequency domain, you will be not able to decode with the high probability correct information out of the single photon. So let's talk a little bit, a few words about the jamming and spoofing. The very first information I'm coming to tell you is that for many years, we were aware that those services, GNSS services, are free of charge. They are very safe to use and so forth. Currently, nobody told us when we buy our cars, navigations, that those are military systems, except Galileo, which is a European one. All other systems are under control of the military. This is including GPS, that belongs to United States of America Army. So this is very important to know, because currently we cannot ensure receiving on the GNSS we use for the stabilization of the oscillators in any part of the world. But furthermore, the new geopolitical situation that is changing near every day is telling us that we have to take into account that GPS might be not available in our country, or it can be jammed, or it can be spoofed. And so let's see shortly how the radio attack can look, and why we haven't noted so far that this problem harms our solution. Because I don't believe there is anybody in this room who will say to me, yes, I experience spoofing. It blocks my network. I couldn't use. So first of all, the time synchronization attack using jamming and spoofing, it belongs to the hybrid kind of attack, which means it is not enough to press a button to generate interference, and that will do a job, definitely. The hybrid attack looks following. First of all, the attacker is interfering the single frequency. In case of Europe, we are experiencing mostly the standard frequency, which is 1.5 gigahertz. That's most of the receivers today they use. But the receivers that have been manufactured in last, let's say, in previous 5 years, they are multi-constellation. So they use other frequencies and more than the one system to survive in case of the jamming. So from time to time, there will be another, let's say, jamming frequency. It can go to the GLONASS, or it can also go to other constellations simultaneously. The final work in the hybrid attack is when all others frequencies are spoofed. So there is no way for the receiver to trust anything. It's currently the receiver is using the control. And believe me, timing is very fundamental for GNSS receivers itself. I mean, the position and navigation are currently secondary functionalities after timing. However, when you consider to define the acronym PNT, GPS, GNSS, are PNT, you will always hear timing on the end. But to launch the position and to compute navigation, you need the timing first and synchronization. So I hope this short presentation, which is now over, gives you a new view to the security, where you can destabilize the complete infrastructure. We are talking here about the distributed architecture, large area, wide area networking application. QKD is one of the, let's say, subsystems of such a big network that should be taken into account for the desynchronization. There are a lot of companies now who are specialized in the synchronization, working on this topic. This remains so far a real Achilles heel for the QKD and other technology. Thank you.
Thank you very much, Tomasz. Very, very interesting. So now we have time for questions. Are there some questions? Okay.
I have a question.
Yes, please.
Can you hear me?
Yes, we can.
Here's Anna Kalisz-Hedegaard. I have a question actually about attacks. I mean, what would be like a minimum synchronization effort, like error that would pass, like that is good enough? Because we're gonna have all those layers, right? So like you will have the classical cybersecurity layer. Then there's going to be a layer of PQC, then QKD. Maybe we're going to have prepare and measure. Maybe we also are going to add entanglement based. I mean, wouldn't that all add up to the synchronization problems because of all those additional layers that will have to between themselves also be synchronized and kind of jump in as a substitute in a moment of an attack?
Yeah, currently, the margin of the error is quite big. I mean, if you focus only on the QKD, we are talking about a high accuracy. Some solutions will require, let's say, a couple of 100 picoseconds. There are some solutions that are now operating on the single picoseconds, even moving to femtosecond level of the synchronization. Of course, if higher synchronization requirement, then the stabilization is more easier because it's all about the noise. I mean, about the techniques to create a noise, to destabilize the frequency. But if you take into consideration the whole network stability, especially cloud, for example, the error margin is very big because cloud, for example, is using the certificates, to protect the communication channels. That's what we currently need the QKD to exchange the symmetric keys. So far, some of the players, they have increased the frequency of changing the symmetric keys of the both sides. So they need some synchronization that was not really important in the past. I mean, having, let's say, a couple of seconds synchronization in the past now has been improved to the microsecond level. We know some players that are experimenting on the nanosecond. I will give you a very exact example. For example, the Equinix, which is one of the leading data centers globally, serving financial markets and London Stock Exchange, Wall Street, and so forth. They have taken care for the internal synchronization of the nanosecond level to ensure a maximum error between the nodes of the Equinix data center, not bigger than 1 microsecond. So if you measure the maximum error between east and west coast of the United States, they will never cross a 1 microsecond. I hope this brings you some idea that synchronization is a kind of a topic that doesn't bring a one answer to your question. You can discuss it neither through the specific technology, QKD, or maybe a certification exchange. The price you pay is mostly blackout of the system. So that's the most worst case scenario. And I mean, a data center blackouts. There are some cases losing control on accessibility to the communication lines for many hours. And this happens to the biggest players in the world anyway. So finalizing, let's say the most small accuracies are required by the public administration to authenticate information, like signing, documents maybe, or some database data and so forth. Did I answer your question?
Yes, thank you for your insights and a great talk.
Thank you.
Thank you. More questions? Okay, I have maybe one short. You mentioned that we should avoid standards for time synchronization. Can you explain why? Because maybe it's not clear to me.
All right. Let me tell you a short story how the thieves tried to steal my car in the past. A few years ago, I had a very modern new car, and it was full of protectors. So thieves came and they break all those protections easily in 1 minute or something. But they did not steal the car because I have installed manually a single ordinary toggle switch, mechanical toggle switch, and they have no idea this toggle switch in my car. So the conclusion is you should always have something extraordinary over the standard. For example, in the military application, they use also, the Bluetooth. Very similar to Bluetooth as we use for the daily business and so forth. But this Bluetooth operates in a different frequency. So it's currently customized for the operation. This is exactly the meaning I have when I'm saying try to avoid the standardization. There is a protocol, standard protocol, high accuracy PTP ETRAP, which belongs to standard IEEE 1588. Let's say a working name is White Rabbit. This standard has been partially born in Poland. Currently, the early baby White Rabbit was in the kindergarten in Poland, and then it has been transferred to CERN to Switzerland. A part of the job was done by company Elproma, a part of the job was done by company Cryotech, which is also a member of this community. And it can achieve accuracy that is fine for the quantum key distribution. But then this is the only currently standard that appoints such standard. So the attacker will assume this is on the board. And if the knowledge of the attacker is high enough, and that's always all about knowing some, backdoors or some gaps, it will be much more easy to destabilize the synchronization than working on the unstandardized version. What we suggest to our customer, we have a technology, for example, as Elproma peak time, that is synchronizing through fibers, dark fibers, on the femtosecond levels, but it is not following any TCP/IP communication. It is just requiring a fiber. The structure is very simultaneous to the quantum key distribution. So every, let's say, distance of 50 to 100 kilometers, you need a kind of a trusted node where you build your repeaters, signal repeaters, and so forth. You need to calibrate to achieve a femtosecond accuracy, but this is possible. Currently, the network presented by ID Quantic presentation, the map of Poland with the QKD deployment, it also includes the very experimental high accuracy synchronization when there are cesium fontaines involved. They ensure very high stability, and time and frequency distribution.